everyone, welcome to day 4 of becoming a data scientist. So today we'll learn more about the population and sample size. So let's get started. So let's understand the concept of population and sampling. For example, suppose in a school there are 10,000 students that studies there and you want to find out the mean time taken for each student to reach school. Now, it's very unfeasible to ask all the 10,000 students about what time they reach school. And instead, we choose 100 students from this 10,000 sample, from this 10,000 population, and we ask them, and maybe we find that the mean time taken for each student is around 30.6 minutes. So, our 10,000 consists of the population, and this 100 people that we selected consist of our sample. Now here are a few terms to get familiar with. So in population, we say the size is denoted by capital N, and for sample we denote it by small n. The mean of the sample is denoted by mu, whereas the mean of the mean of the population is denoted by mu, whereas the mean of the sample is denoted by x bar. The variance is given by sigma square, and the formula is here where we subtract each data point in the population from the by mean, and then we divide it by the total number of the population size, and the variance for sample is given equally. So here is the sample size where we take the square of each of the sample from their mean, that is x bar, and then we divided it by n minus 1. Okay, now coming to sampling distributions, let's go back to our original example. So here we have selected some randomly 100 students from our population sample, from the population size, and the average mean commute time we found it to be around 30.6. However, we are uncertain whether this sample mean accurately represents the true population mean or not. The sample mean might not perfectly reflect the population mean due to possible flaws in the sampling process. For instance, if the sample included too many people with unusually high commute times, the sample mean would be skewed. To address this uncertainty, surveys often provide a range of values. For example, we might estimate that the true population mean is between 30.6 plus minus 5 minutes. This range accounts for the possibility of sampling error that could cause the sample mean to overestimate or underestimate the true mean by up to 5 minutes. If the range were narrower, such as plus minus 1 minute, we could be more confident that the actual average is close to 30.6 minutes. Conversely, a wider range like plus minus 10 minutes would make us less confident about the proximity of the sample mean to the true population mean. To determine how much our estimate might be off by and to understand the range of possible sample means, we use the concept of sampling distributions. Now let's switch to a simpler example to illustrate this. I hope you remember that we actually studied an example in the first lecture that involved a game played by 10 different people of picking out a red ball from a bag of mixture of red and blue balls. To estimate the average number of red ball, you can randomly select 5 people out of those 10 people and record the number of red balls each collected and calculate their average. Now, if you remember, we got the average as 2 red balls in that experiment. Now, if we repeat this with 5 people, suppose we get that the average ball as 2.8 red ball per person. This result might differ from the actual known population mean due to sampling variability. Now, if you repeat this process many times, each time taking a new sample of 5 players and calculating their average, you will generate a range of sampling means. Now, plotting this means will give a graph something like this. here we have the samples, and here is our PDF, the probability distribution function. We'll give a graph something like this. This distribution helps us understand how sample means vary around the population mean. The sampling distribution has important properties that will be covered in the next lecture, and these properties allow us to estimate the sampling errors and understand the reliability of our sample practices. In practice, while sampling distribution are crucial for understanding the small-scale examples, such as our game with 10 players of picking out red balls, they become even more important when dealing with larger populations like 10,000 students in a school. And by understanding the sampling distribution through smaller examples, we better grasp how to apply these concepts to large-scale scenarios. Now, as we increase the number of samples, so here are the different plots for different number of samples, the sample mean, which is denoted by x bar, becomes increasingly closer to our population mean, denoted by mu. This happens because taking a larger number of samples reduces sampling bias and better represents the diversity of the population. When comparing the sample distribution with different sample sizes, for example, if we sampled with a sample size of 20 or 10, say, the distribution of the sample means is narrower and more concentrated around the mean compared to the distribution when we have taken the sample size of 5. This is because the larger sample provide a more accurate estimate of the population mean, leading to less variability in the sample means. Now, the standard deviation of the sampling distribution is also known as the standard error and is given by, so standard error is given by the standard deviation divided by square root of number of samples, where sigma is of course the standard deviation in sample size. Now, this value is what we observe from our sampling is very close to the value that we have observed. The standard error actually indicates the typical distance between the sample mean and the population mean. The smaller the standard error means the sample means are closely packed around the population mean, which suggests more accurate estimates. Conversely, a large standard error means that the sample means are more spread out, leading to less reliable estimate. Now, low standard error, now you see for sample size more than 30, so here are the sample sizes which is more than 30, the distributions, it reaches the normal distribution regardless of the underlying population distribution. In a sense, this is called the central limit theorem. And it states that the sampling distribution becomes approximately normal as the sample size increases, even if the population distribution is not normal. This is the fundamental principle in statistics and is used to make inferences about population parameters based on sample data. Now, coming back to the question, how can we go from the sample mean to population mean? Now, let's take a sample size of 100. Now, since it's already more than 30, we know that this curve is normal. Now, for practical reason, if we consider that the standard deviation for this distribution is 10 and we have the sample size of 100, then the standard error is given by 10 by root over 100, which is equal to 1. Now, since our sample size is 100, which is greater than 30, we can safely approximate that the sampling distribution is normal distribution, as I just said. So, thus the sampling distribution can be modeled as normal distribution with an unknown mean mu and a standard error of 1. Now, to determine the probability that the sample mean, which is 30.6 that we assumed, falls within a certain range, such as say plus minus 2 minutes of the population mean, we use the properties of the normal distribution. We know that the standard error is 1. Now, if we want to find the probability that the sample mean is within 2 standard deviation of the mean, that is plus minus 2 minutes of the population mean, therefore there is a 95.4% chance that it lies within 2 standard deviation from the 1, 2, 3 rule that we have seen in the previous lecture. We use the standard error to calculate the confidence interval for our sample mean of 30.6 and the margin of plus minus 2 minutes. Therefore, the confidence interval can be written as 30.6 plus minus 2. This means, in other words, that the population mean will fall within the range of 32.6 and 28.6 with a confidence of 95.4%. Now again, to summarize, the confidence level represents how confident we are that the true population mean lies within our confidence interval. In this case, the confidence interval is 95.4%. Now, the margin of error, which is the maximum amount by which we expect our sample mean to differ from the population mean. In this example, the margin of error is 2 minutes. So, to generalize, if you know the sample mean as x bar and the sample standard deviation, which is denoted by small s, and the sample size, which is denoted by n, the confidence interval can be calculated as x bar plus minus z star multiplied by the sample standard deviation by root over of sample size, where z star is the z-score corresponding to the desired confidence level. Now, some of the very commonly used z-scores are given as follows. So, for 90% confidence, the z-score is plus minus 1.65. For 95% confidence, the z-score is plus minus 1.96. And for 99% confidence, the z-score is plus minus 2.58. So, to reiterate how to go from sample mean to population mean. We can do the following steps. So, number 1 is take a sample size of n. Then number 2 is take or find the mean of the sample and standard deviation. And now you can say for y% confidence, that can be anything that you can put, for example 90 or 95 or 99 according to our problem statement, is given by x minus z star s by root over n and x plus z star s by root over n. Now you can only do this with the assumption of the central limit theorem. So central limit theorem lets you assume that the sample mean would be normally distributed with a population mean of mu and standard deviation of, or standard error of, sigma by root n. Using this assumption, it becomes possible to find many things such as margin of error, confidence level, etc. Okay, now let's quickly understand the concept with the help of a quick example. So for example, you maybe taken data from the food company where they say that some amount of chemical in the food should be below 2.5 ppm. Now from the population you choose a sample size of 100 and the sample, and you say that the mean is 2.3. The standard deviation is 0.3, and since it's a food company, you want to be absolutely sure, so you take the confidence interval as 99%. So what should be the confidence interval? So it should be, according to our formula, so it should be x bar plus minus z score into standard deviation by the sample size. Now z score for 99% confidence, from here you can see that as 2.58. So if we plug it and 2.58, we get the confidence interval as 2.223 and 2.377. So we can say with 99% confidence that the population mean lies between 2.3 plus minus 2.223 and 2.377. So that means it lies within the safe zone, and this the chemical content in that food is lower than 2.5